you. Always exciting to be here. We need to take a bit of energy. It's the last session of the day. I really appreciate you being here. So this is going to go a bit like this. We will start really slow. We go a bit technical, but then we end up slow. So we will have plenty of time to let everything sink in. I don't know if there are any people from NVIDIA here right now. OK, there's one. Oof, OK, this doesn't put any pressure on me at all. So welcome. My name is Luca, and I got totally nerd snipe last year. I'm mostly working as an AI or ML engineer, as it would say like a couple of years ago, into trying to understand what are the kind of requirements in terms of memory and computation for these huge large language model to be hosted both like locally on your machine, but also by some other huge providers. So all of these field trips started out when I was reading a blog post by Cursor, who, by the way, just got like a 900 million CDC round yesterday. So this is one of the OG blog posts back when they weren't just announcing how many they got. Congrats to them, props to them. And this post got me started with all of this history, like this trip. Basically, they say, and by far the most intriguing bit is this one, Llama is best for prompt-dominated tasks such as classification, and might also make sense when your workload has no prompt tokens. And like, what does this mean, right, to have no prompt tokens? And all of this got me started into trying to understand how this model works, how much memory requirements they have, and how basically the GPU is used. So today we're going to go a bit on like this. We will talk usually about disclaimers and credits, because they very well do, and then we immediately jump straight away to the takeaways, right? So that we know where we're headed. And then we will start building the technical part. We're starting about trying to frame the context and then doing like a mock example with the simple neural network. And here is where we will start getting technical with drawings and animated drawings, right? So we do it like back to the school board. And then afterwards, it would have been like a Blackbody. I would have used that, but alas, I didn't know. We will talk about transformers finally, right? Like at the middle of the talk, and then finally we will draw the conclusion, like properly, and further expand on the takeaways, right? And do an implication of all was the stuff that I went through, and what this has to do with serving models at scale. All clear? Okay, I don't see people yet sleeping, so that's a good sign. Talk about disclaimers. There will be plenty of simplifications. This talk is mostly about giving you rules of thumbs and intuition about how to compute requirements to host one of such models. And it mostly draws from a video called Street Fighting Transformers by Professor Sasharash, who I think now is actually working at Cursor doing reinforcement learning. He built this amazing YouTube video about like half an hour-ish or so about how to do these kind of calculations, which is basically the first half of my talk. And his talk is inspired by yet another book called Street Fighting Mathematics, about like doing guesstimates for optimization problems. So there's like a huge tradition of these funny ways to get like good at guesstimating. And this has been incredibly rewarding for me in the sense that it makes you think about how to approach these problems and gives you the intuition to quickly understand how big, how large, how intensive this is. And so throughout this, we'll deliver and talk about 3 things and 3 main conclusions. The first one being hardware, and like the next generation of optimizations to run this model very fast is developing algorithms that are aware of how the software, the hardware they're running on is designed. The second conclusion is that inference and training are dramatically different in terms of requirements of computation and memory. And finally, that there are different use cases for which you might want to self-host a model. Could be for your company, compared against using one in like an enterprise setting, like calling OpenAI or any other model provider. So, and these were actually the conclusion, right? And in the end, all of this boils down to the fact that when you talk about training, is that model training can be parallelized, whereas inference cannot, just as much. And if you need to undergo a certain trade-off and need to accept whether you want more latency or utilize the hardware more. So all of this is going to talk about, revolve around these points, and around mostly 3 quantities that we're going to discuss when we talk about a large language model or any actually transformer-based model. the number of parameters, the memory, so the number of VRAM you actually need to have to host the model, and finally the compute, so the number of operations that are going to happen throughout when you use those models. We will forget all of the units of measurement, generally. So we're trying to be like as unitlessy as possible, but you can also go into that. And we're also going to investigate 2 dimensions mostly, training and inference. There's also going to be fine-tuning, but we pretend that doesn't exist because it's already complicated enough. So 3 key takeaways, and we're going to analyze those through those lenses, okay? And we'll try to move and approximately get there going through this, starting from the very vanilla neural network. So here is the technical part. We will go slowly because we have plenty of time to dry you out. But I promise I will try not to make you late for the happy hour event. So let's get started. This is a neural network, right? It has 2 parameters in, 3 parameters out. How do we count the parameters? How many does this have? Well, it looks kind of interesting. When somebody gets through the input, it has to be passed through all the other intermediate activations in the other layer. So if we want to count the number of parameters, of course, there would be 6 neurons during training, 6 neurons during inference. Fairly easy, right? We can represent this neural network in a different way using this projection notation, whereas instead of writing, like drawing every circle for every neuron in and out, we will just draw a straight line. So this doesn't change anything. This is how we represent it. Any neural network with D1, D2 has like D1 upsi times D2 parameters in, and they are, of course, the same during both inference and training and inference. This is fairly easy, right? So we move from the concrete example, 6 neurons to D1 times D2. And this is just it, like this is a number of parameters. What if we want to understand the compute requirements of such a neural network? Well, it's really easy, right? When we talk about training, of course, we want to learn these parameters that we associate to each neuron. So basically, we will do a forward step, which means basically doing enough operations to go through every neuron in the first layer and in the second layer. So basically what will happen is we have our input, which could be 1 vector that will go through D1 and D2. So basically we need to perform D1 times D2 operations, right? Did I already lose you? I know it's kind of like, did we get to this one, right? Yes, okay. Now that's the energy, okay. The cool thing is that GPUs are amazing machines. They are so good at parallelizing stuff. So instead of passing just 1 vector in, we can pass a batch of vectors inside. It is actually sometimes faster to just do a matrix-matrix multiplication than a vector-matrix multiplication. So it's really easy for us to exploit this hardware and pass a batch of inputs. So our forward step, like we're going on and taking all the vectors and make them go through the network, will just require B times D1 times D2 operations, flops, which means like multiplication between every element of the input vector and every neuron in the layer. And the same goes for inference when we want to make, like to use the model that we learn the parameters to yield a prediction, right? But there's actually one difference between training and inference in that when we do train, we want to learn the parameters. So we also need to do the so-called backward pass or do gradient descent and basically have the model learn through seeing the examples one after the other. So basically, and here we immediately see the difference that during training, we significantly need more memory in general as a rule of thumb than in inference. And in particular, we might need 3 times as much memory as in inference. So, and we start to see immediately that when we want to train a model, we have different computational requirements than when we run inference. And this is going to matter a lot when we move from a really simple neural network up to a transformer model, such as an LLM. When we talk about compute, the difference, of course, we already talked about batch size, but why does training require 3 times as much compute? Well, the bottom line is you, of course, need to do the forward pass, but you also need to do the backward pass and compute the derivatives of the loss function with respect to both the weights that we have and also the intermediate inputs. It's just a general rule of thumb. But to keep the rule of thumb clear, ideally, you can say that you need to have add 2 times as much as your network dimension in terms of computations. Memory is the 3rd dimension that we're going to take a look into it. In terms of inference, it's a bit different. We always need to have, well, we need to store into the memory of our machine all the parameters. But we also need to be able to host this called B, like the batch size, times D2, which is basically at least B times D2, which is the dimension of the widest layer inside the architecture. This is because if you think about it, when our vector goes through the neural network, it goes through every layer. So technically, we could have a model like taking the input, make it go through D1, and then make these intermediate inputs go through like the D2 layer. And in our already example that we have here, D2 is much bigger than D1. So basically, as soon as we compute D2, we can discard the stuff that we have computed for D1 and free up a bit of memory. This might not always be the case, but as a general rule of thumb, we know that our model kind of requires just as much memory just to keep the whole set of parameters into it, plus at least the biggest layer that you have in your neural network. And if some of you try to host a model on your own, for example, say, back in the days it was Mistral, now it's any Quen model, you would likely do this kind of exercise. Like, if the model has 7 billion parameters, you will need like 2 times as much plus 20%. We're going to explain why it's plus 20% in a bit, but this includes like the 2 times the number of parameters just because the conversion from number of parameters to memory in terms of gigabytes. So if you go 7 times 2, 14 gigabytes of RAM, plus a 20%, which is used for one thing we will see in the end, but also to keep the largest activation in memory. So this is partly where it comes from. So in a way, just as a recap, when we do training, there is one thing that happens, is that we need to go through all the forward step. The forward step happens also in inference when we do computation. Computation is more demanding, which means we need to do more operations during training because we also need to train the model. So we need to compute some derivatives. So the forward step needs to be followed by a backward step, that's the training phase, 3 times more expensive than regular inference, as a rule of thumb, right? When we look, and this is all the compute, when we look at inference time, it's a bit easier, it's a bit less than you would usually expect. There is always going to be the amount of parameters that the model has that needs to be in memory, but you also need to store in, when it comes to inference, the batch size, so the number of examples you're passing through, times the dimension of the largest layer, at least, as a rule of thumb, always. Training is a bit different. You're always going to need to have all of the parameters in memory, but due to the way that these models learn, you will also need to store all of the activations. This stems naturally from the fact that we need to do back propagation, so we need to compute the derivatives across all the layers of the neural network. So we need to have all of the intermediate activations, which means the result of the multiplication of the input times every layer. So the input x times d1 give you like the intermediate input or the activation of d1, and then you multiply this activation by d2. You also need to keep that into memory when you do training. But it doesn't end here. You will also need to store 2 times like as much memory as 2 times the number of parameters in general, because we will use a specific optimizer that is called Adam, and the optimizer is what basically tells you how much to adjust by how much you want to adjust the parameters when you learn. There's a lot of stuff to digest, and it's not going to get easier after this one. I'm sorry about this one, but the gist of it is that we need to keep in mind all of these scenarios, but the idea is inference and training are dramatically different in terms of requirements because, of course, during training, we need to make the whole learning happen. So we need to run the backward pass, which requires many more computations and also requires much more memory because we need to store all the intermediate activation, all of them, plus retain like an additional parameters, like an additional amount of memory that is equal to the number of parameters that the model has in order to compute by how much we need to adjust every weight in the neural network. How is this going? Okay, I still see some ends, not as much as before, I'm sorry, but feel free to stop by afterwards. This is it took me a while to learn this thing. This is like the second time I'm doing this, and I've been rehearsing this at least 3 times with my colleagues. So it took me a while for me to learn this as well. Please do refer to the sources as they go through really slowly about this. You don't have to be able to remember all the figures, just remember the colors, but just as an idea, it is important for you to keep in mind that training is different from inference. Inference requires less compute and less memory in general. So we need to think of them when we design our infrastructure to train them differently. And it was basically memory. Okay. But now we were going to talk about LLMs, right? Right? There have been so many talks about like the transformer architecture, like yesterday during the tutorials. There's going to be one tomorrow about the internal. So I won't go really long about this one. So this was actually the transformer architecture from the original paper that has an encoder and a decoder, and doesn't have like the angry eyes, of course. It can see, but in a different way. And here we're just taking a bit of it, the encoder part, but we're not really concerned about this. But if we want to understand like how it is made, we have 3 elements, mostly 3 building blocks, the input embedding, and let's pretend that the positional encoding comes with that. And then, there we go, n times, like the gray rectangle, yes, it is it gray? Yeah, it kind of looks white, but I swear it's gray, that contains the feed-forward layer, so the thing on the top, plus the attention mechanism that is here in the multi-head attention. So basically, ChatGPT and any model that looks like it is mostly, I'm doing some simplification here, made of the input layer that does the embedding thing. So basically it translates your input after it's been tokenized into a vectorial representation. So basically every element in the sequence of text that it gets is transformed into a sequence of numbers, a vector. And then it goes through n attention blocks, each of which adds peculiar meaning to it. How many of you know what a transformer is? Oh, few, okay, I was hoping you get lost. But in the end, and we will see when we go through the drawings, but the bottom line, just to give you anybody who hasn't some context, is that this attention mechanism is a way to assign importance, to compute a weighted sum of all the words that come before it when we're talking about text generation to the word that we are going to use it. So basically, to predict the next word, we are actually looking at the word we are currently at, and the transform mechanism is just a weighted sum of all the words that come before it. And what the neural network does is that it learns how much weight to give to every word behind it. So if you will, we take the input sequence, and we transform into a bunch of vectors, and when we make them through these n layers, we are basically going through and tweaking these weights so that the words that are mostly related with the one that we are currently trying to predict have a much bigger weight. The classical example of this is, I don't know, the quick brown fox jump over the lazy dog. When we look at lazy or fox, actually fox will be better. Fox will have stronger connection between quick and brown, but less with lazy, because lazy is related to the dog. So in a way, the transformer architecture is a way to mathematically learn mathematically what we inherently know as like analyzing sequences and knowing which attributes or which adjective refers to which part of a sentence. So in a way, this weighted sum, I'm getting a little off sidetrack, I'm sorry about this one, but the whole point of attention is to find which word are closer, more relevant for the one we are trying to, they are actually going on to predict the next one. And so what happens is that across all these n layer, we are enriching this representation, trying to find out which words are more important for the other one. I did a really poor job about this. I think you can watch all the talks that have been happening like yesterday and tomorrow, especially like the keynote today was also about this, but to put everybody on a kind of a same page. This is a bit dense, but the idea that this mechanism, it basically boils down to the input encoding and then weighted sums, as you would do to assign a score, like give like a final ranking to somebody like doing exams now the school is over. And the embedding layer is really easy to deal with when it comes to computing all to computing all its computation and memory requirements. A number of parameters of course is v times d. Basically, we have all the vocabulary, all the words that we want to predict, to be able to predict, times d, which is the dimension of the embeddings that we want to get with. Ideally, for example, be like, I don't know, a vocabulary such as ChatGPT 4.0 has something around 200,000 of vocabulary size, which basically means its vocabulary is made up of 200,000 sub-pieces of words. And d is the projection, basically is the number of dimensions that we want our vector to be, how much long we want our vector to be, which is around like in the thousands, ideally. So maybe 4,000 dimensions, or maybe even less than 4,000 dimensions. And when it comes to computation, actually, this is totally negligible because we are just basically looking into like a word and say, oh, this is the vector associated with this word. So this is really easy. And when it comes to training, of course, we need to store in memory requirements. Of course, for inference, we will need to store the parameters. For training, we also need to store the state of the optimizer. So this is really easy part. We can pretend this doesn't exist when we do all the computation. When we look at the feed-forward layer, well, this basically kind of looks like what we have already seen in the very simple example before, except usually it has like a more complex shape where it goes through what is called the hidden dimension, which is usually 4 times the dimension of the embeddings. So basically, this is by just from the original paper. It's been like a sort of a tradition that everybody does it in this way, mostly. But ideally, basically, you go through like a much bigger representation, then you squeeze it back so that you get meaning. Ooh, wow. It was long, I need to rush this one, it's understood. So basically, the number of parameters of this feed-forward block is n times, where n is the number of blocks that you have, times all of the multiplication. It's 2 times 4d times d, because of course we need to go 4d to 4d, and it is the same number of parameters that we go from 4d to d. So basically, we just lamma 2 times above it. The computation in memory is the same as the neural network we saw before, so we're really fine. The attention layer is a whole different beast. And we can represent it, and it kind of looks scary, but if you squint, you see that actually it is made up of the same structure that we were seeing before. It has 2 elements that are basically MLPs, so what we've seen so far, plus the squiggly line in the middle. So we have this 3D because of the way the token is represented is projected into 3 dimensions. I won't go into this because the previous talks and tutorials have done an excellent job in explaining what they are, but basically it's a way that we assign weight of the most relevant words for the one we are currently looking at. And then basically, so when we want to compute the amount of memory and computation required for these layers, it's pretty trivial because we saw it so far. So we just count up the number of parameters. When we talk about the memory of compute, it's the usual neural network. So when we do the forward layer, we need to keep all the parameters into memory. We need to just do 1 step for the forward. When we're doing training, we also need to do the backward step. Self-attention is really magical, and this is where everything boils down to. Self-attention is really peculiar in that it has no parameters because it's just a weighted average, a weighted sum. But the compute requirement is a bit more complex because it needs to go every word in the sequence, one after the other. So for the batch that we have in input, we need to go through the element number 0, the element number 1. Sorry, I'm doing Pythonic indexing now. So the first word, the second word, the third word, going on. And we need to do this computation for every element of the sequence. So this T is really important, and it will be really important going on. So keep in mind. When we talk about compute, it becomes a bit easier. So we look at the whole attention block altogether. We know that when we want to estimate the number of computation required, we just do what we have done so far. So d times 3d is the MLP, the forward step. We need to go through all of the elements of the sequence to compute the attention. Then we also need to do d times d because it's another MLP, and yet again another MLP on top. We need to multiply this times the batch size, the number of blocks that we have in the attention architecture, plus the sequence length on its own. And if we are doing training, we also need to multiply this by 3. So if we have a model, this is where it starts to get bigger, right? Especially because there is a multiplication of t times t. But the point is that when we do training, it's really easy to parallelize this kind of operation because we all know everything beforehand. So for example, when I want to predict the next word, I'm basically just, I know the whole thing. I know all the data that I want to train my model on. So I want to train it to predict the next word, but I already know the next word. So it's really easy to train this model, such as I can input every sequence and already know the answer. This is not going to be the same thing when we do inference in real time, so keep in mind into that. When it comes to memory, of course, we need to store all the parameters, plus twice as much for the optimizer state, plus all of the activation for this block. So this fancy multiplication that's appearing here is basically anything that we saw so far. We do not have a multiplication in the parentheses, just an addition, but that's basically what we saw so far. It looks more complex, but in the end, I'm just adding every parameters that we have in a really simple neural network. When we do inference, we of course need to store every parameter. There we go. Plus any, of course, multiply for any number of blocks that we have inside times the batch size. And finally, we have this really t times t. When we develop this equation, we see that t times t becomes t squared. And this is where everybody says that transformer is quadratic in terms of computation. And this is basically a way of saying it's slow. It requires a lot of time. Not slow, but it requires more time than you would. And this is basically the intuition, because at inference time, this implies that when we generate a token, we need to wait after the whole model is done to generate the next one. And this is basically where you will see your ChatGPT model when you prompt it. It will just stay idle for a second and then start generating text one by one, and you will see it appear one by one. This was actually happening. It cannot generate the whole thing together as a block. Actually, it can return everything just as a complete answer, but it's better for us to see that it's generating one token at a time. But in the end, this is really what's happening, just generating one token, one word at a time. Not really one letter at a time, not really one word, but still, it's going on one by one. And this is why it's taking time. And this is everything that boils down to it. Because in the end, we need to wait for token T to be generated before generating the next one. But engineers found a way to increase the memory usage so that we can have faster generations. And basically, this is called KV cache, but everything boils down to the fact that when we want to compute attention, we can keep the key and value. So basically, 2 out of the 3 values that we can generate for every single word can be stored in memory. And then we only need to compute Q for the next step. So we store all the key V for the previous steps in the memory and append the new ones that we compute when we do each new subsequent generation. This, in practice, translates into one thing, that the memory requirements are much bigger, the number of parameters, of course, the larger activation, as we saw before, but we also need to add the amount of parameters that we keep in mind for the KV cache, the intermediate activation, for not really intermediate activation of the KV cache, but that's whatever. And inference engines, so the service that we use to serve these machine learning models with, and which we call and return our responses, implement a much more sophisticated variant of this mechanism. And basically, this has a really neat implication if you think about it. When we do training, we can grasp and get a feel that what needs to happen is really different. And as an engineer, to optimize memory usage of our GPUs, or to save time, basically, we need to adopt 2 different strategies. During training, it's really easy to parallelize everything. Because self-attention is computed efficiently, because we already know the T+1 word that we're going to predict. And so this is a neat implication for how we compute the KV values. However, during inference, we always need to wait for a generation to append the values to the KV cache. And also, we need to wait a bit, but we can be a bit more clever about how we do it. This is a serious implication, and I think I don't have time to go on, so feel free to chat about those afterwards. But basically, this has a really neat implication that we see every day when we chat with GPT. When we ask a question, we usually have to wait a brief amount of time before the first bit of the answer gets shipped to us. And this is because the KV cache, this is actually called in fancy terms the time to first token. But this basically means that when you ask the model your question first, the whole model computes the KV cache, does the so-called pre-fill of all the query and the key and values inside the cache, and then starts generating afterwards. So the first step is really optimizing the GPU usage, whereas the second step happens autoregressively. We cannot do away with this step. We need to be slow with this one. But since we're using the KV cache, we can be much faster, because otherwise we will have to go back to the beginning of the sequence and compute again every key and value So if you take like a 100 token long sequence, we need to do like this first token, and then we need to go to the second token and compute it for the first one and the second one, and then go to the third one. We compute the query and the key and the value for the first, the second, and the third, so on and so forth. With the KV cache, when we get to the third token, we already have some values for the first and the second already stored. So we only compute the new one, and we append it to memory, and we go on and on like this. We save a lot of memory, like we save a lot of computation, but we increase the amount of memory we use. And this was the hard part, and we can optimize a bit more the memory usage when we do inference, still for the autoregressive side, but there won't be time for this. The point is that this has general implication if you remember to go back to the first task. You might want to self-host model for your industrial application if you are able to shove a lot of stuff into the prefill phase and optimize how much memory you can use of the GPU like this, in that way, in the first part. And then you don't really care how slow you generate the subsequent tokens because you're working asynchronously. If you remember, like OpenAI has like a so-called batch mode, whereas you will just send them the prompts and within 24 hours they will give you back the results. That's because they're doing this. They're really being clever about how they optimize the utilization of the hardware, and then decoding only when they have like at this time without any constraint in terms of how fast they need to ship their responses. When you have a really long prompt and when you want the model to return a really short answer like yes or no or classify something, but when you tell them please write a report about so and so on and so forth, and it has to generate like several thousand tokens possibly, this is really not the kind of task that you want to run your models on average. Of course, we can be really clever about this, but as a rule of thumb, it's really worth it to use self-hosting when you perform these batch processing jobs, or you have prompts that are like that dominate the amount of generation you need to do. So that your prefill phase can basically just like most of the work that you need to do for inference. In the end, though, you need to run your own experiments and see if your own use cases is suited for which one of the two. Of course, needs vary. We work with any size of company, from small ones to bigger ones. In the end, you need to be able to run your own benchmark and assess how much memory to use for every one of those. This was like a really tense one, but I just wanted to show you this, right? That intrinsically, running this transformers architecture is really hard, not really hard, but can be really complex in terms of what happens if you're trying to train them or serve them. And these operators like OpenAI or any other model provider has sophisticated infrastructure and has to manage the amount of requests that they get in and route them to the most efficient use, like with their North Pole, basically. The North Star is just how much well they can utilize the GPU. And when it comes to training, it's a whole different beast. But when it comes to inference, we found clever tricks by which we can increase the amount of memory we use to reduce the number of computation and yield the results, basically the responses and the generation faster. And this boils down to a clever trick, which is called the KV cache. And in the end, it's really great to be able to self-host your own models, especially if you're working locally, like code agents or playing around. It's really worth it. But translating this to an enterprise setting requires a lot of experimentation. And it's a really fine art, and it's really fascinating. But really to you to get your hands dirty and know a bit more about these rules of thumb to understand how model works. It was a lot of work, but if you would like to connect and share any feedback how this went, and if you have any follow-up question, I would love to get in touch with you. And thank you very much.